All right, so let's go ahead and start the notes for section 2.5, working with truth tables. Okay. Sorry, almost ready here. Get centered. All right, what we're going to be doing in this section is looking at how we can start building truth tables. We've introduced the idea of truth tables a little bit earlier when we were introducing, our compounds, statements, and things like that. What we're going to be doing today is going more in depth with truth tables and using them to actually analyze something. Okay. Okay, so let's go ahead and take a look at that. Derek, I think your mic is on. You might want to mute until you have a question.
Sorry about that.
No worries. Okay, so first let's look at a complex statement. So when we're looking at statements, we first need to be able to break them apart and translate them into symbols. That's going to be our first step in taking something verbal or written and analyzing it with our logic tools, because we want to make sure that things look are in symbols. We did this in the last unit also when we were translating things into like a math equation, right? So in 1.1, when we were working with percentages, we said, okay, when I read this sentence, if I translate everything exactly over into math symbols, then I can solve an equation and get my answer. Okay, so we have a similar idea here, except we're not looking at an algebraic statement. We're looking at a logical statement, right, in symbols. Okay, so we want to make sure that we can identify what are the keywords that let us know what symbol or connector to use and things like that. So let's look at this example. If I go to class and do not fall asleep, then I will play video games later. All right. So the first thing we're going to do is identify some simple statements. So I have this simple statement. I go to class. We'll call that P. Okay. We have this simple statement. We're going to be a little bit careful about this, right? We have I do not fall asleep, but we said earlier that when we are making our statements, to avoid confusion, especially with things like double negatives, we're always going to make our simple statements a positive statement about something that is, not something that is not. So I'm not going to make my Q, I do not fall asleep. I'm going to make my statement Q, I fall asleep. Okay. It's not that it would be wrong to say I do not fall asleep as Q, but first of all, if we're always consistent, then that's less confusing. And secondly, if we were to throw another negative in there somewhere, when we're computing stuff, it can get extra confusing with double negatives. So if we keep our statements as positive, it's usually going to be the easier way to go. Then finally, my last simple statement, I will play video games later. So we'll just call that little r. Okay. Now we have to identify what connectives we have. And I notice that there's more than one of them in here, because I can see if then, but I also see this and in here, and those are both connectives. Okay. So what we want to do is say, all right, well, what's sort of like the main one over the whole sentence, okay, and which one is sort of like inside things. Okay. So if I read this again, if I go to class and I do not fall asleep, then I'll play video games later. So it feels like I have a big if-then, and inside my if-then I have this and statement. So our main connector is going to be the if-then. Okay, and remember that the if-then, we use an arrow. Okay. So I have if some piece, then some other piece. All right. So now we're going to look for the parts that are joined by that connector. Okay. What we want to do when we're looking at an if-then is not look for what comes first in the sentence. And in this case, it's not a problem. But in logic, right, this first part, the antecedent, is going to be the part associated with the if. When we're saying a sentence in English, you can move phrases around and keep the same sentence meaning. Okay, and we'll look at examples of that later. But the key is to look for what's connected to the if and what's connected to the then. In particular, the if, because oftentimes the then can be left off on an if-then statement. When we're saying or writing something. Okay, so we want to look for the part between the if and the then. Okay. Okay, so the if part, right, the part that comes after the if, or that's sort of, if, then I have a blank, is going to be I go to class and do not fall asleep. Okay, and since I go to class is P and I fall asleep is Q, then I can write I go to class as P. The symbol for and, right, was this caret-shaped thing. And I do not fall asleep, okay, I have a not in there, so it's like the negation of the simple statement I fall asleep. So I'm going to put in not Q. Okay, so this is writing my symbols for this, and you can start to see why we want to be very careful when we're breaking this down, because things can start to look complicated fast. Okay. Also, this is probably very new for most of you, right? These symbols you're not used to. When we're doing algebra stuff, you might take it for granted, the fact that you know what adding and subtracting and multiplying and dividing look like in all their various forms, and you're very used to them. So when you see them in a math equation, you know what to expect. Okay, these are symbols that you're not used to because you haven't had a lot of time practicing with them, right? Algebra, you've spent years practicing with. You may not have enjoyed it, but you've done it, right? Okay. The second part is the part that comes after the then, right? Okay. And the then part, right, after then we say, it says, I will play video games later. Okay. Well, I play video games later, that's just R. So what we're going to do is we're going to put those into the blanks because we've identified the main connector for the if-then. I have the if part in symbols, and I have the then part in symbols. Okay, so we put these into the blanks, so then I have P and not Q, right? And then I have my arrow, and then R. Okay, so I could read this as if P and not Q, then R. Okay, other words that we have for that are P and not Q implies R. Okay, that's maybe less common to use. The if then is a little bit more clear, but the implies lines up with a word matches a symbol exactly, whereas the if then, we don't really have a symbol for the if and then. They're combined with this arrow. Okay, both are fine. Okay, so the steps we followed to symbolize the sentence, right, to translate it from words into symbols, is we started by identifying the simple statements. Okay, remember that they should be positive. Okay. we'll use the not, right, which has the symbol tilde, okay, if necessary, like we had for our second simple statement, okay, to make it line up. Then the next thing we did is we identified and symbolized the main connector. Okay, so that's our process of breaking it down. We take the main connector, and then we can look at the other pieces, right? So this splits the original sentence into two parts. Okay. Then we take each part and we repeat, right? We symbolize each part as its own statement. Okay, so if one of those parts had a connector with other complicated parts inside, then we would just keep breaking it down, right? What we're doing is we're looking for the main connector over the whole piece, and then when we look at the parts, we look for the main connector of that part, okay? And if those have other pieces inside them, right, we look for the next main connector, right? And we just keep breaking it down into smaller and smaller pieces till we get down to our simple statements. Okay, so that's the process of turning our sentence from words into symbols, right? Symbolizing a complex sentence. Okay, so let's look at another example. All right, so we're going to symbolize this statement. If Kermit is a frog, then he's either green or blue, and he's not blue. So let's look at the simple statements. And once again, what I'm going to do is I'm just going to read through and find a piece, right? So, you know, I have this if Kermit is a frog, so that's going to be my first one. Just call it P. Kermit is a frog. Okay. Then he's green. So I'll just say Q is that Kermit is green. Suppose I gotta use blue for this next one. Or blue, I want to be clear about this, so I'm going to say that R is that Kermit is blue. So he's either green or blue is the same as saying that Kermit is green or Kermit is blue. When we write the sentence, we're a little bit more concise, but when writing the simple statements, you know, we want to be clear about what we're using here. And sometimes if you use pronouns, if there was more than one subject, then that could be confusing. Okay, and he's not blue. Well, Kermit is blue is already written down as a simple statement, so he's not blue doesn't need its own symbol. It's already there, right? That's just going to be not R. All right, so now let's identify what our main connector is. Okay. Maybe what we can do is start by looking at how many connectors we have, right? So if I'm looking at my connectors, we have this if-then, they go together. So that's one connector. I see an or, that's two. I see an and, that's three. So I count three connectors, right? So we have if-then, right? So that's one. Okay. We have or, that's a second one. And we have and, that's a third one. Okay, so what we need to do is figure out like which one is the main connector, right? How do I know what is inside what or where things go? And when we're looking at a sentence written in English, it's the punctuation that sort of lets us know how things fall. When we're writing it in symbols, we can use parentheses, but you don't use parentheses when you're writing sentences, right? So we have punctuation instead. So the punctuation helps us identify that and is the main connector. Okay. And the way that we're doing this is by looking at the commas. Okay. So I have my if-then, and this or is part of the then statement, but the comma breaks the sentence. Okay. So sometimes, when we write if-then, there's a comma built into the if-then. Okay. But commas also break the sentence. So I have my if-then, and then I have what comes afterwards. Okay. So if I look at how the sentence is broken up, the comma tells me I have something and something else. That gives me my main connector. Okay. So I'm going to have an and statement, and I have stuff before and after it. Okay. Before that main connector, right, before the and, I'm looking at what I have. I'm going to go ahead and write it out. Okay. So we have the complex statement, if Kermit is a frog, then he's either blue or green. Okay. I'm sorry, I have those backwards. He's either green or blue. Let's not switch things around. I don't know. Things getting confusing here. Okay, so the main connector here is the if-then. Okay. So if I symbolize that, what I have is stuff, right? If stuff, then other stuff. Okay. Now remember that in my whole sentence, this was the left side of the and statement. So I can say, okay, put all of this in parentheses and whatever's to the right. Okay. So that's how I'm breaking it down. I started with my main connector, and then I look at what's inside each piece and say, can that be broken down further? So on the left, we had a complex statement, this if-then that we broke down. Okay. And in between the if and the and, right, the if part, okay, the if part is Kermit is a frog. Okay. So that's symbolized with a P. Right. The then part is he's either green or blue. Okay. Well, Kermit is green is a simple statement. Okay, that I believe was Q. And Kermit is blue is a simple statement R. They're connected with an or. So I could write this as Q or, and then Kermit is blue, I think was R. Okay. So for our if-then part, our if part is P, then in parentheses Q or R. Okay. All right. So that's like our if-then part. So that this part is this part is this part. So now let's finish it right after the main connector. Right. If I go back up, our main connector was and. After that and, we have he's not blue. Okay. So after the main connector, we have he's not blue. Okay, and we can symbolize that. Remember, we want to use positive statements. So Kermit is blue is one of our basic statements. So Kermit is not blue would be not R. So we're going to use that tilde for not R. So now we can finish our whole thing, right? On the left of our and statement, we came up with these symbols, right? If P, then Q or R. Okay. Then I put a parenthesis around that whole thing and say and I have not R. Okay. This would have also been correct if I didn't put the parentheses here. I actually don't need them. And the question is, when do I need parentheses, right? So let's answer that next. When do we need parentheses? This is another place where in algebra you sort of take that for granted, right? You kind of know how parentheses work. So we're going to take a minute to figure out how they work in logic. And it's the same basic idea. They tell you, this is the order to do things in. Okay. But that means that there has to be some sort of like natural hierarchy for what to do next. All right. So we need parentheses whenever we have more than one connector joining two statements. We do not need parentheses around a not statement. Okay. So we could just write not R on its own instead of parentheses not R above. Okay. And we don't need parentheses around the whole final statement. Okay. So these parentheses are unnecessary. Okay. And I certainly don't need parentheses around the whole big statement. That's not going to do anything. Okay. For the other stuff, I think the easy way is just to say, well, if there's a compound piece, you put it in parentheses, and then that's very clear. Okay. All right. So let's look at another example. Symbolize the statement, it is not the case that if Jake learns to juggle, then he will win the talent contest. Okay. So we're going to start the same way that we did before. Right? Our step one is to identify the simple statements. Okay. So I'm just going to read through the sentence. It says, it is not the case that if Jake learns to juggle. So that's the first thing that we're actually saying, right? All of that other language, right? Okay. It is not the case is just a big way of saying not, okay? But we want a positive statement, so I don't need that. And then, my if then is going to be a connector, okay? So Jake learns to juggle is the first part of this that's actually saying something. So my P is Jake learns to juggle. Then he will win the talent contest. So that's going to be Q. Okay. So the statement begins with this phrase, it is not the case that. Okay. Right? Which negates the rest of the statement. So what we're going to do is say, if we say it is not the case that, and I say a bunch of stuff, then what I want is a not that bunch of stuff. Okay. So the statement that we're negating is everything that follows. So if Jake learns to juggle, then he will win the contest. Okay. So when I read this, I can see that this is an if-then statement, which we symbolize with an arrow. Jake learns to juggle is P. He will win the talent contest is Q. So then our whole statement we said was not, and then we have that inside part. And we said that inside part is this P arrow Q, right? If P, then Q. So our whole statement now is going to be not if P, then Q. Okay. All right, so far all we're doing is practicing how to symbolize a statement. How do we go from our language into symbols? And that's really key. Okay, and I'm trying to go through this slowly and methodically because this is, I think, one of the more challenging parts about doing logic is correctly, translating things over. And then once things are translated over, right, then, what follows is going to be a little bit, it's going to be a little bit easier. It's a little bit more algorithmic. All right. So let's go through an example, and let's write down everything that we would do, right, as we're problem solving, right? So here's another example. If Kate finishes the homework and does well on the exam, then she will not need the extra credit and will go out on Friday night. Okay. So once again, we want to start by identifying the simple statements. Okay. So the first thing that I encounter is Kate finishes the homework. Then I see a connector, so I'm going to stop. So my P is Kate finishes the homework. Okay. The next part, still talking about Kate, does well on the exam. So that'll be our Q. Okay. We have our connector if then. We're ignoring that for now because we're just looking for simple statements. Okay. Then she will not need the extra credit. And then I see an and, so I'm going to stop here because that's a connector, right? So that makes a compound statement. So I'm done with my simple statement. So my R, remember we want to make it a positive statement, so I'm going to leave off the not. I'll just say Kate needs the extra credit. Okay. And then the last piece, Kate will go out on Friday night. Just keep running through the alphabet, so we'll call that one S. Okay, now we get to the challenging portion. We need to figure out how the sentence is broken up. And again, the key that we have in written language is the punctuation. Okay, so I see a comma here. That's the only comma I see in the sentence. that breaks the sentence into two pieces. Okay, so I want those to be two separate pieces. And the way that they're connected, right, the left and right side, the left side is if portion and the right side is a then portion. So I'm using an if then to connect them. So this is my main connector. Okay, so the comma splits the sentence. So I can say, all right, I have this if then. So now let's look at the left side of the if then. Kate finishes the homework and does well on the exam. So I've already written down Kate finishes the homework as P. My connector is and. Does well on the exam is Q. Okay. Now I look at the right side of the if then. She will not need the extra credit and will go out on Friday night. So I see that the connector there is an and. She will not need the extra credit is the negation of R, so that's not R. Kate will go out on Friday night is S. Okay, so I don't expect that when you're doing problems for the second and third and fourth time that you will rewrite out these statements over and over again. Okay. What we want to do is write out what are P, Q, R, and S, identify the connectors, and you can build your sentence here. Now notice that I didn't write this from left to right. I didn't start with a parentheses, P and Q parentheses. Okay. I started by figuring out what the main connector was. Okay. After I got my simple statements, I identify the main connector, and I put the two sides of that main connector in parentheses, and then figure out what's inside. Okay. Yeah, so maybe a quick review of our symbols. So and was symbolized with this caret pointing up, or is symbolized with caret pointing down. The if then is symbolized with an arrow. If and only if is a double arrow, and not is that tilde. Okay, so that's just a quick reminder of our symbols. I think that maybe on this homework and probably the ones that follow, it might be helpful to sort of have this written down somewhere, maybe on like on a note card to reference as you're going through to make sure that you're not mixing them up, especially the and the or can be confusing because it's like the same symbol just flipped upside down. The way that I remember it, the and is not quite, but almost like shaped like a staple, like it's gonna like hold these two statements together, whereas the or looks like it's kind of a wedge dividing the two apart. I don't know, that makes me think of the and the or. If that doesn't work for you though, don't you know, whatever it takes. A note card is probably a good thing. You can reference the note card even when you're taking the test, so I mean there's no need to get too crazy with it. Okay. Now let's look at building a truth table. Like I said, we started truth tables a little bit when we first introduced each of the connectors. We filled out some truth values. So if you know a little bit of what a truth table is, what we're going to do now is build a truth table for one of these big complex statements. Okay. So the idea is once we've symbolized a complex statement, we're going to construct a truth table for that complex statement. And what it's going to do is it's going to tell us under what conditions is your complex statement true or false based on when the simple statements are true or false. Okay, so we need to remember rules for our truth table. So I want to start by going through the each of our symbols and you know a way to remember you know what they do. Okay, so we have negations. That's the not, right? That's the symbol for that is the tilde. So if we have a negation, it flips the truth value. So it's false if the original statement is true. It's true if the original statement is false. Okay. We have conjunctions, which are like an and statement. We have other words for it too, right? We sort of brainstormed a whole list of words that meant the same thing. But we can think of these as and statements, and our symbol for that, right? The and statement is true if both of the original statements are true, and it's false otherwise. Okay, so if they're both true, the and statement is true. If one or both of them are false, then the and statement is false. Okay. Disjunctions are like or statements, and we're going to write the symbol for that. The disjunction is false if both of the original statements are false. It's true if I have one or more truths, right? If anything is true in there, the or statement is true. Okay. Then we have a conditional statement. That's our if-then, right? Symbol's an arrow. Okay. That one was really tricky, but the way to think about it in a truth table, there's really only one situation where a conditional is false. It's false if the antecedent, which is the if part, is true, and the consequent, which is the then part, is false. It is true under all other situations. So the only way that an if-then statement is going to be false, right? If I say if A, then B, so if you do have A, but I didn't deliver on B, then the if-then statement is false. Under any other circumstances, the if-then statement is true. Okay. Biconditionals are the most complicated sounding one, but I think that they're very easy in practice, right? So this is the if and only if. Okay, the symbol for that is going to be a double arrow. Okay, it's true if the original statements match, if they're both the same truth value. Right? So either both true or both false, either way, the biconditional is true. It's false if they don't match, if they're different. Right? One's true and one is false. It doesn't matter which one. Okay, so that's our rules, and I'll come back and reference this, but let's go ahead and look at a statement, and we're going to construct a truth table for it. So Alice has a cat, but not a dog. I want to go through the same steps that we started with before to symbolize the statement. So Alice has a cat. Okay, that's a simple statement, so I'll say that that's P. Okay, and then but not a dog. You know, but is a connective word. Remember that when we were looking at our other things for conjunctions, right? But is a word that kind of means the same thing as and. It has a different connotation, right? A different, you know, a flavor in our English language, but it still connects in the same way. All right, so our next statement, Q, we want to be a positive statement, so we're not going to say Alice does not have a dog. We're going to make our simple statement, Alice has a dog. Okay, so then if I want to symbolize the statement, our connective, but is a conjunction. Okay, on the left side we have Alice has a cat, P, and on the right side, Alice does not have a dog, so that's not Q. Okay. And what we talked about with parentheses, I don't need a parenthesis around just a P by itself, so I can get rid of that one. And we said you don't need parentheses around the negation of a statement. Okay, that's just going to be glued right on there. So we can actually get rid of all of these parentheses. Okay. If you left them on, it would not be wrong. It would just be extra. And we don't need to make things any more complicated than they have to be. So we can leave those off. But notice that as I'm constructing it, I started with the parentheses. I started with parenthesis and parenthesis. And that's just my good habits that I've built in, right? When I'm breaking it down, I start by putting things in parentheses, and then I look inside to see is what I have a simple or a complex statement. Okay, so we have two simple statements. So our truth table will need 2 to the power of 2 or 4 rows. Okay, so we have this pre-built truth table here with 4 rows. Okay. And what we're going to do is start off by listing the possible combinations of true and false for our two simple statements. Okay. The way that I like to do this, I guess there's more than one way to think about it. I'm going to try to always make my truth tables start the exact same way, okay, with our combinations of P and Q being true and false. Because if we're always consistent with it, then I think that makes things less confusing. So one way to look at it is I go to the last statement that we have and just alternate trues and falses. Okay. Or another way to look at it is I take my first thing and say, suppose this is true, what are all the possibilities? So if P is true, then Q could either be true or false. So those are both situations where P is true, right? P is true and Q could be true. P is true and Q could be false. Now I look at all the possibilities when my first simple statement is false. So P could be false, and then Q could either be true or Q could be false. Okay, now what we need to do is we need to label the columns, right? What do we need to write here? And the goal behind a truth table is to break things down into simple pieces. So when we're working with a truth table, we only ever want to be doing one thing at a time, one connective or one, out of our list of symbols, we only ever want to work with one at a time. Okay. Now, the not statement is unique in that it applies to a single thing. All the other ones combine two things together. So for any step, we either want to be applying not to one existing column, or we want to be applying one of our connectives to two existing columns. Okay. So we're going to need a column for negation of a simple statement, right? So I have in my statement not Q, so we're going to need a not Q. Okay. But we don't need not P because that doesn't come up in the end. There's nowhere where it shows up. So we don't need the not P. Okay, so I'm going to put the not Q as one of my columns. All right. And then now I have all of the right-hand side of my connective and all of the left-hand side. And now I'm worried that this above is going to look confusing. Okay, we'll just take that back out. I'm combining these two with an and. That's one connective joining two things that I know. Okay, so we're going to create a column for that combination. Okay, so in this problem, the entire statement we're looking for is all that's left. Okay, so I put the whole statement, P and not Q. All right, so now what we're going to do is we're going to fill those in using the rules above. So remember the not said that it just changes the truth value. It's just the opposite. So I'm going to look at the Q column and I'm going to just make sure I have the opposite truth values. Where I see a true, the not Q is false. Where I see a false, the not Q is true. Right? I have a true, so this is false. I have a false, so this is true. The AND connector is true when both the things it's connecting are true and false otherwise. And what I'm connecting is the P column and the not Q column. So I only look at those two columns, and I say, all right, let's connect them. For the first row, they're not both true, so I get a false. Okay. For the second row, they're both true, so the and statement is true. Okay. For the third row, I don't have both true. I have at least one false, so it's false. And for the fourth row, I have at least one false, right? I don't have both true, so it's false. So that's it. That's my truth table. I have filled out a truth table for the statement, Alice has a cat but not a dog. Okay. And we'll talk about analyzing these more later, but I noticed that the only way that my statement is true is this row. That means that the only way for that statement to be true is for the P statement to be true and the Q statement to be false. Any other combination does not make my statement true, right? So what is that? Well, when P is true, that means that Alice has a cat. When Q is false, that means that Alice has a dog is false. So that sort of makes sense, right? Like, oh, of course, if Alice has a cat and she does not have a dog, then the statement Alice has a cat, not a dog, will be a true statement. Okay. And in any other situation, Alice has a cat but not a dog would be a false statement. Okay, we'll look at analysis more later. Let's focus on figuring out how to build these truth tables before we figure out what they do for us. All right, so multiple connectors. We might have a more complex statement, okay? And what we're going to do here is skip the part where we symbolize the statement. We're just going to jump right into how do I build a truth table for this, okay? Just because we want to focus on that, okay? So in this example, we're just looking at the statement abstractly. We don't have any English sentence to connect it back to. All right. So if I look at it, the number of simple statements, I see P, Q, there's Q again, there's P again. So I have two simple statements. Okay. So my truth table needs 2 squared or 4 rows. Okay. So when I build my truth table, I need 4 rows. Okay. So I'll have my column headers. Okay. And then I need P, I need Q, and that's all of my simple statements. So let's go ahead and fill in the truth values, and you could just remember a pattern. This is another thing that you could just look up every time, okay? But we'll fill this out as true, true, false, false, true, false, true, false. Same as we had before. So, all right. Once again, what we want to do is look at our statement and figure out what we need, starting with the negations of our simple statements. Okay. So when I look at my original thing, I can see a not P, but I don't have a not Q. This is not a not Q, and this is not a not Q. So for our simple statements, we need the not P, but we don't use the not Q. Okay, so I'm going to put a not P in here. Next, let's work from the inside out, right? The innermost parentheses. 2 parentheses, right? So my left side of parentheses, I have not P, which is already a column that exists. Q already exists. They're connected with an if-then. So if I look at the on the left, okay, we have this not if not P then Q. Okay, then on the right, and the left and right don't really matter. I'm just trying to keep them separate. We have Q if and only if P. Okay. Inside of those parentheses, we're combining two columns that we have. So on the left, I see not P, which is a column that exists, Q, which is a column that exists. I can combine those with an if-then. Okay. So that's going to be a row of my, sorry, a column of my truth table. Not P implies Q. Okay. Here, both Q and P are columns that already exist in the truth table, so I can join them with a connector, right? So we can have Q if and only if P. Okay. Next, we look for negations of those arguments, right? So, or those statements, rather. So on my left one, outside the parenthesis, there wasn't anything, right? The parenthesis inside, everything was taken care of on the inside. But on the right-hand side, I have this not symbol on my parentheses, so I want to be able to negate that whole thing. Okay, so we have not, and then in parentheses, Q if and only if P. And the Q if and only if P is a column that now exists in our truth table. So once we figure out the truth values for that, it's going to be a column that exists. So then we can negate it, and that's just doing one thing. Okay. Now all that's left is the outermost thing is this or, and it's combining things that now already exist, right? On the left I have this guy, okay, and then on the right, if I take this whole thing, I have this guy, and I can join them with an or. So the only thing I have left is the whole statement altogether. Okay. So not P implies Q in parentheses, or not Q if and only if P. Okay. Now, my preference is to figure out the column headers first, and then to go in and fill out the truth values. Because I find that if I switch back and forth, I get confused more easily. Other people find I figure out a column header, let's fill out the truth tables for that right now. Figure out a column header, figure out the truth table. Okay, either one is fine. You just gotta pick what works best for you. And like I said, I like to fill out all of the column headers first so that everything is set up. And now I can go and fill in truth values. Okay, and that's like computing. Okay, and then I can, maybe go and grab maybe I would put like this information on my note card also, right? Once I know what the symbols are, and then I also know how to compute with them. Okay, so not P, we're going to flip the truth values on P, so the truths become falses. The falses become trues. Okay, now I have not, if not P, then Q, and this is the tricky one. Be very careful with your conditionals. So I'm starting with the not P. Okay, and as a reminder, conditional, and if then is false if the if part is true and the then part is false. So if this first part is true, that only happens down here, and the then part is false, I get a false. Okay. So if the if part is false, I automatically get a true. The if part is false, I get a true. If true, then true gives me a true. If the if part is true and the then part is false, that's when the if then gives me a false. This is by far the most tricky one. This one takes, you have to be careful with it, and it takes practice before it, will feel like it makes sense. You have to be very careful, right? Because it's not, it's not always left to right. It's what's the if part, what's the then part. Okay, the if and only if is a lot easier. Do they match, right? True, true, they match, it's true. True, false, they don't match, it's false. Okay. Do they match? Nope, false. Do they match? Yes, they match. It's true. Both falses is still a match. Okay. The next one, I'm negating the column that I have immediately to the left here, right? This one. So I just flip the truth values. So I'll get false, true, true, false. Okay. And then my last step, I'm going to take my pink arrow column, and on the right-hand side I have my green arrow column, and I'm connecting them with an or statement, right? And again, if we just remind ourselves, the or statement is false if both the things we're connecting are false, and true otherwise. Okay. So in this first one, they're not both false. I have at least one true, so it's true. Both true, so it's true. They're both true, so it's true. The last one, they're both false. That's when the or statement gives me a false. Okay, so that's our truth table. So it was a very complicated statement, but it only had two simple statements. Any questions so far? All right. All right, so now let's look at what do we do when we have quantified statements, right? So we want to use truth tables to analyze deductive arguments. Often those have quantified premises, like some or all or none. Okay, how do we symbolize those? Okay, so what we can do is we're going to break this into parts. First, we're going to look at a universal statement. We can turn a universal statement into a compound statement by looking at like a particular instance, right? We're going to maybe it's easier to talk about with an example, but we're going to instantiate it. Okay, so we're going to apply it to an arbitrary thing. Okay, so to do this, right, let's first go back and look at our basic truth tables, right? So if I start with P and Q, these were the truth values that we had for P and Q, P or Q, if P then Q, P if and only if Q. Okay? And we did these earlier when we introduced the connectives, okay? We did each one separate, and then we built this truth table. So this comes directly from our notes on, I forget which section now. Okay, now let's look at this statement. All birds can fly. I can sort of look at this as being two simple statements. Okay, I can say, all right, one piece of this is that this thing is a bird, right? And another piece of this statement is that this thing can fly. Okay, so instead of talking about birds and what they can do, what we're doing here is we're saying, all right, take an arbitrary object, and I don't know what that object is, and let's see, okay, is this thing a bird? Can this thing fly? And we'll talk about those as separate pieces. Okay. All right. Now let's look at a truth table to see how these statements interact with each other, right? So if I say the statement, all birds can fly, okay, and my thing is a bird and my thing can fly, okay, then we sound like we're good so far, right? Then all birds can fly. Yeah, that sounds right. If my thing is a bird and it can't fly, then that clearly shows that the statement all birds can fly is false. Okay. If my thing is not a bird and it can fly, well, that's a possibility, right? Like, okay, yeah, if all birds can fly, I might have something that's not a bird and that can fly, and that can happen. That's fine. And if I pick something that's not a bird and can't fly, well, yeah, that can happen too, right? So under the situation where all birds can fly, I can pick something that's not a bird and can't fly. That's fine. Okay. So when I look at this, when P is true and Q is true, this thing is a bird that can fly. Right. And so that's consistent with all birds can fly, right? So that's where we get our true. When P is true and Q is false, this thing is a bird that can't fly. Okay. So all birds can fly, and I have a thing that's a bird that can't fly, that doesn't work. That's not consistent, right? So my statement, all birds can fly, would be false, right? So that's where my false comes from. All right. If I pick something that's not a bird and can fly, if my thing is, or I should say, isn't a bird and can fly, okay, then the statement, all birds can fly can be true, and you can still have something that isn't a bird and can fly, right? So that's fine. And likewise, if I pick a thing that isn't a bird and can't fly, okay, that is fine when I have all birds can fly. It's okay that there are things that are not birds that can't fly. That's still true. Okay, so that's just sort of being very explicit about where we get our true, false, true, true. Okay, what I want to do is look at these at the same time. This is the statement, all birds can fly, and look at the truth values, true, false, true, true. What we want to do is say, do we have truth values that match up to that in our truth table? And I would say, yes, we do. There I see the true, false, true, true. So I get the same truth value out of if P then Q as I do out of this quantified statement, right? All birds can fly. So if my quantified statement, all birds can fly, is, right, all P, right, or Q, that gives me the same truth values as if P then Q. Okay. So what we can do is we can symbolize all birds can fly as if P then Q, meaning if a thing is a bird, okay, then it can fly. So this is how we're going to deal with quantifiers. We can treat, and so far this is just the all that we've dealt with, but we can treat this all quantifier as an if-then statement. So if I have all P are Q, then I can just write, okay, use if P then Q. Okay. Now, what if I have a negative universal, right? No of something, none of something. So we can also represent a negative universal as a compound statement, right? So we're going to go through the same process. No fish can fly. So what I'm going to do is I'm going to say I have two basic statements, right? We'll say P is that this thing is a fish. we'll say that Q is this thing can fly. Okay. So if P is true, then the thing is a fish, and Q is true, then that means that the thing can fly, right? So this thing is a fish that can fly. Okay. Can no fish can fly be true if something like that exists? Right? No. Right? So then I know that this would be false. All right. What if P is true and Q is false? So I have this thing is a fish and it can't fly. Okay. Can no fish can fly be true with a thing like that? Well, if I pick out a fish that can't fly, when I say no fish can fly, right, that's consistent with each other. Yes, we're okay there. Okay, so in that situation, we're fine. What if P is false? So my thing isn't a fish. Okay, true. Q is true, so this thing isn't a fish and can fly. Okay, so can the statement no fish can fly be true with a thing like that? Right? Well, I can certainly imagine that if no fish can fly, there are things that are not fish that could fly. That seems fine. Okay. What if P is false and Q is true? Then P is false means this thing isn't a fish. Oh, I think we have a typo here. This should be a false. Okay. P is false and Q is true. This thing isn't a fish and can't fly. Okay. Well, can no fish can fly be true with a thing like that? Well, if something isn't a fish and can't fly, yeah, I could imagine that is fine under the situation where no fish can fly. All right. False, true, true, true. Go back and look at my little table that I've built. Do any of these match? Do any of them say false and then 3 trues? I do not see that. Okay. So we have a little bit of a problem with the negative universal. Okay. Here's, okay. We don't have a truth table that matches exactly. Okay. Close does not count, all right? But maybe we can make an adjustment, right? So our truth table is true in 3 rows and false in 1 row. Okay, so if I just look for other things that are true in 3 rows and false in 1, well, the or statement is true in 3 rows and false in 1. The if-then statement is true in 3 rows and false in 1, just different rows. Right? Okay. So let's look at the or statement a little bit more closely. And what I'm going to do is I'm going to fill out a truth value, and I'm going to look at all the different ways that we can combine it with negations. Okay. So what we're going to do is we're going to just experiment a little bit. Okay. So I'm going to throw in a not P. I'm going to throw in a not Q. Okay. And the whole bit. So the not P, negate the P's, negate the Q's. Okay. And now let's combine some things. So here we have P or Q. So remember the or statement. If I have any truths, the or statement is true. I have at least one true. I have at least one true. When they're both false, that's when the or statement is false. Okay. Here, I'm combining the not P and the Q. So I'm combining these two. Okay. So I have at least one true. They're both false, so this one is false. I have at least one true, and I have at least one true. Okay. Next, I'm taking the P and the not Q. They're far apart, so we got to be careful here. Right? I'm going to highlight them temporarily. Okay. So I need the I need to check and see, do I have at least one true? Yeah, true and or false. It's at least one true. At least one true. Here they're both true. Here I have two falses, so I get a false. And here I have at least one true. Okay. And now we have not P. We're combining it with the not Q using the or. Okay. Two falses gives me a false. At least one true, at least one true, at least one true. All right. So I have a match here. Our no fish can fly was false and then three trues. And here I have found something that is false and then three trues. So we can symbolize no fish can fly as not P or not Q, meaning a thing either isn't a fish or can't fly. Okay. So another way of looking at no fish can fly is to say, if I have a thing that exists, it's either not a fish or it can't fly. Okay. So we can symbolize none of something. It's just a little bit more complicated, right? Okay. So if I have no A or B, I would have not A or not B. Okay. We're getting there. We're almost done. I think we have 2 more pages of notes. Symbolizing conditionals. Okay, so there's a lot of different ways that we can phrase the same conditional. So let's look at this statement. If I am thinking of 4, then I am thinking of an even number. Okay, so one way to look at this is if P then Q, where P is the statement I'm thinking of 4, and Q is the statement I'm thinking of an even number, right? So if I were translating into symbols, this is probably what we would end up with. Okay. But in English, we could rewrite this same statement, right, the same sentence a lot of different ways. Okay. So if I'm thinking of 4, then I'm thinking of an even number. What I want to do is say the same thing using slightly different words. So if I am thinking of 4, I am thinking of an even number. So we left out the then. Okay, and that's very common. Okay. I am thinking of an even number if I'm thinking of 4. So the if is still on the I'm thinking of 4 part, just like we had in our original. Okay, we just rearranged the the pieces of our sentence. Okay, so here we wrote the if part second. Okay, and it's still the same sentence. All right, we can also use, remember when we were looking at if then, we talked about some different words that we could use for this. I'm thinking of 4 only if I'm thinking of an even number. So here, only if is introducing us to what the then part is. Okay, and that can be confusing. Okay, so we have to be careful. Only if has a different meaning than if. Sort of backwards. Okay, but we alluded to that a little bit when we introduced the biconditional, if and only if, right? So it's giving you, it's saying that this piece is an if piece and a then piece. All right. Only if I'm thinking of an even number, I'm thinking of the number 4. Okay. Now that's probably a more confusing way to write this. We're getting into something that you'd probably be less likely to run into. Okay. The only if still introduces the then part. Okay, and just like we had before in this second one, we can sort of flip the pieces of the sentence around and it keeps the same meaning. Okay, so the only if introduces the then part even if we switch the order. Okay. The number I'm thinking of being even is necessary to it being 4. This isn't something that I think that you would run into like when you're, at a coffee shop talking with your friends. This is a very mathy way of thinking about it. When you're talking to mathematicians, then sometimes they talk like this. Okay, so all right, so this is a very mathy phrasing. Necessary is the then part. Okay, so the number I'm thinking of being even, right, and is necessary. Okay, so that's still the number being even is necessary. Okay, to it being 4. All right. The number I'm thinking of being 4 is sufficient to it being even. So I'm thinking of 4 is sufficient, so that sufficient is telling me what the if part is. Okay. And again, sufficient and necessary are a really mathy way of describing things that we don't see as often. All right, let's look at an example. Symbolize this sentence. Okay, I will do the homework only if I am not too tired. So our simple statements are, I do the homework. Okay, we'll say that that's P. The other simple statement, I'm too tired. Q, remember that we want to keep our statements positive, so the not part will come in as a not. All right, so the phrase only if, remember that introduces the then part of an if then. Okay, so the only if is introducing the I'm not too tired, which is not Q. So my statement would be, because I can see that it's a then, not Q is the then part. I have if P, then not Q. Right? I'll do the homework. P, so if P, then not Q. So another way to look at this, we understand this to mean that if I really do my homework, okay, then I must not have been too tired. Okay, so it's kind of another way to look at it, right? When you say, I will do the homework only if I'm not too tired, you're sort of looking into the future and saying, okay, if I'm not too tired, then I will do my homework. But another way to think about that is after the fact, if you did your homework or not. Well, if I do my homework, then I must not have been too tired. All right. We're on our last page for the day, so stick with me here. Let's look at some types of statements. When we create a truth table, we have different things that can happen as a result, right? So this is the sort of analysis part, okay? We want to look at the result of our truth table, okay? So what we're going to do is let's fill out this truth table and then see what happens, right? So I have P, if and only if, and then I have this compound statement, not Q or P. So remember, we wanted to start by looking at whether or not we have any negations of our simple statements. Is there a not P or a not Q in here? And there aren't any, okay? So then I work into my inmost parentheses. So my inmost parentheses is Q or P, okay? That parentheses has a negation on it, so I want to have not Q or P. And then the only thing left is my whole statement. P, if and only if, not Q or P. Okay, so now let's fill out the truth values. So Q or P, the or statement, as long as I have at least one true, is true. So we get true, at least one true, at least one true. They're both false, so the or statement is false. For the not, I look at my existing column and just flip the truth values. So not Q or P, I look at the Q or P column and I flip all of the truth values. Okay. For the if and only if, I'm going to take two existing columns. So I have my P column and I have my not Q or P column. The if and only if is really just asking, do they match? Right? So true, false, not a match. True, false, not a match. False, false, that's a match. False, true, not a match. Okay, so my compound statement that we've created, P if and only if not Q or P, this statement can either be true or false, depending on the truth values of P and Q. A statement like this is called contingent. Okay, so and anything is a possible result, right? What we said could be true or could be false depending on the statements P and Q. Okay, let's look at another example. P, if P and Q, then P. So I don't have any negations of my simple statements P or Q, so I go to my parentheses. I have P and Q, and once that's done, the only thing left is my whole statement. Okay. So let's combine the P and Q columns with an and. Remember, I need both of them to be true for the and to be true. If either one is false, the and statement is false. Okay, and now I'm going to take my two existing columns, P and Q, and P, I'm combining them with an if-then. Here we have to be careful. If true, then true gives me a true. If I have an if-then, the only way for an if-then to be false is to say if something that's true, then something that's false. So when an if-then starts with a false, it's automatically, the if-then statement is automatically true. Okay, so in my final result, my statement is true no matter what. So this statement's always true no matter what the values of P and Q have. Statements like this are called a tautology. Okay. So an example would be like somebody said, well, that may or may not be. That statement doesn't really tell me anything. Of course, everything either is or isn't, right? It's not telling me anything. Okay. Statements that are always true no matter what are called a tautology. Okay, and they're not really telling you anything about P and Q because it doesn't matter what P and Q are, right? It's always true. All right, let's look at another example. P and Q, if and only if, not P or not Q. So when I want to build this truth table, once again, we want to start by looking for negations of simple statements. So we have a not P, we have a not Q, so I'm going to need both of those. Then I look at my parentheses. Okay. On the left, I have P and Q. Inside parentheses, those are two existing columns. On the right, I already have an existing column for these negations, so I'm going to join them with an or. So not P or not Q. It's joining two existing columns with an or. And now I have the whole left side of my if and only if, and I have my whole right side of the if and only if as existing columns, so then I can join them with the if and only if. Okay. So let's fill out the truth table. Not P, we'll flip the truth values on P. Not Q, we'll flip the truth values on Q. So now we have the AND statement. So when they're both true, I get a true. If either one is false, I get a false. Here I have a false. And here I have a false. Now I want to look at the not P, the not Q column and join them with an OR. So I'm looking at these two columns and I'm joining them with an OR. That means either one of them can be true. It's only false when they're both false. And first row, they're both false. Now I have at least one true. I have at least one true, so it's true. And I have at least one true, so it's true. Okay. Now I'm going to take these two columns that I have from the parentheses and join them with an if and only if. It's really asking, do they match? So true, false, not a match. False, true, not a match. False, true, not a match. False, true, not a match. Okay, so my compound statement that we've created is always false. Statement is always false, no matter what the truth values are for P and Q. So it doesn't matter what statements you come up with for P and Q, like Kermit is a frog and dogs are beautiful. It doesn't matter what my statement is. My compound statement is always going to end up being false. It doesn't matter what P and Q are. Okay. A statement like this is called a contradiction. Okay. So this is like our first piece of analysis where we are coming up with some conclusion about a statement. Okay. And this is going to be important to what we're going to look at later with arguments. Okay. But we need to take things in pieces. So even though this seems like, okay, why do I care if it's, contingent or tautology or contradiction? We'll get to why that's more important later. Right now what we're doing is we're just saying this gives us some information about our compound statement. Okay. And remember, we're doing this analysis without any context. I don't need to know what the statements P and Q are in order to say something about this compound statement. Okay, so that's what we're trying to get at, to eventually get at the structure of an argument. All right, that's it for the set of notes and for today, and I apologize. I know that we normally go from 9 to 10 and we're way over, but this was a longer set, and that's all right. Okay, so next week we're gonna have notes